Hi, we're going to finish up Unit 6, Relationships Within Triangles, as we talk about the triangle inequality theorem, and we'll also take a look at what's known as the hinge theorem. You know what a hinge looks like on a door, and we'll talk about how that relates within a triangle and relates to side lengths and angle measures. So let's get started by looking on GeoGebra. We're going to take a look at the connection between side lengths and angle measures. I'd like you to take a look as we explore that together and see what kind of connections we see between the side lengths and the angle measures within a triangle. So within this exploration, it asks us to list the sides in order from shortest to longest, and also the angles in order from smallest to largest. So why don't you do that, please, and restart the video when you're ready. Okay, so maybe we notice that the side lengths, I'm going to number them from shortest to longest. So BC was the shortest, followed by AB, and then CA. Then when we take a look at the angles from smallest to largest, angle A is the smallest, followed by angle C, and then angle B. So did you notice any connections there with those? Maybe you noticed that opposite sides and angles were matching up. Let's see if that holds true. So as we change this triangle, I'm going to switch this up a little bit, and we'll look at the angle measures now. So here I have where's the shortest side? Over here, 1, longest side, so shortest to longest, and then if that's true, our opposite angle, this should be our shortest, our smallest angle, next smallest, and then third smallest. So it appears that our conjecture follows through that the opposite angle and opposite sides match up. So our biggest angle will be opposite the biggest side. Our smallest side or smallest angle is across from each other. Okay? So that's the relationship between side lengths and angle measures. You might want to write some of that information down, maybe even draw a little sketch of a triangle, and maybe just list some random measures. This is 90, maybe this is 30, and this is 60, and just give some measurements. Where is the longest side going to be? Over here across from the right angle. Where is the shortest side going to be? Well, that would be across from the shortest or smallest angle. Okay, just something to help you remember that. Let's do this practice problem. I want you to list the sides of triangle RST in order from shortest to longest. Pause the video and start it when you're ready to check the answer. So shortest side have to be across from the smallest angle. So ST would be the shortest, followed by the next shortest angle is 30 across from RS, and then the biggest angle, biggest side, RT. Okay. So here is that connection once again. The theorem is written down. You can copy that. I believe I gave that in your notes. You can highlight any of the important information. Just keep in mind if I have two sides, AB and BC, well, I know angle C is going to be greater than angle A because it has the bigger side across from it. Same way, 50 degrees compared to 30 degrees, I know this side will be longer because it has the bigger angle across from it. Let's take a look now at the triangle inequality theorem. Okay, so we're exploring on GeoGebra again, and we want to take a look at the triangle inequality theorem. And basically what that means is we're trying to find which segment lengths can combine to give us a triangle. Okay, so if I have segment lengths of 3.9, let's make it an even 4, an even 5, and an even 6. We form a triangle with segments of 4, 5, and 6. So I can take my triangle and move it around and find that I've got a meeting spot here. That forms a triangle. I could even move those down. I have to scroll up here. Oops. And I could find a triangle that fits that way too. So no matter which way I could swing those around, I would form a triangle. Fix that up. Okay. All right. Now, if we take a look at this, let's try other different segment lengths. So let's go with 2, let's go with 4 and 6. If I use 2, 4, and 6, those arms aren't going to fit very well together. Not quite reaching. You can see the circle showing all the different places that this will reach, and can't quite form a triangle until they're right on top of each other, stacked right on top of each other. So there's a connection there with the side lengths, and we got to find out, well, what's going to help me form a side length? Well, if I make that one 5.5, now it'll fit. So maybe you're noticing something about 2 of the side lengths. Well, 2 of the side lengths need to be longer than the third side length, because otherwise, as we had this case with 2, 4, and 6, when they're equal, well, they only fit if they are stacked right on top of each other. And if I have 2, 2, and 6, you can clearly see that those 2 arms aren't going to reach anywhere. So 2 sides need to be longer than the third side, is the basic understanding of the triangle inequality theorem. The sum of any 2 sides must be greater than the third. And we'll write that down in our notes later on. The next thing we want to figure out is different ranges we can have for triangle lengths. So if this is my triangle, what are the different possibilities I can have for side F? If I have a side FD, which is length E, FE, which is length D. Notice, what are the possibilities? Well, the shortest I could have is if they're stacked right on top of each other, and that's not a triangle. But if I'm just slightly larger than that, and then the longest that side gets is if they're almost stacked right next to each other, those 2 side lengths. It's not a triangle, but now it is. It's slightly a very large obtuse angle here at angle F. So you see a connection between measurement E and D. What is true about those 2 side lengths? Well, if D plus E, if these 2 segments are added up, we know that that third side has to be slightly smaller than that, because that's as far as it could be, and that's not a triangle. And if we bring that arm back down, we see that segment D, the full segment, minus E, whatever this one is, gives us the remaining segment F. And we know it has to be greater than F, because right now at measurement F, it's not a triangle, but slightly bigger it is now. So slightly bigger than the difference of the 2, but less than the sum of the 2 other side lengths. We'll write that down now in our notes. Let's put that down in our notes here. The triangle inequality theorem. So the sum of any lengths of any 2 sides of a triangle is greater than the length of the third side. So as I mentioned, 2 sides, AB and BC, need to be bigger than AC. And AC plus AB need to be bigger than BC. And then AC plus BC need to be bigger than AB. So any 2 sides need to be larger than the third side in order for all 3 to connect and form a triangle. So now we can apply what we figured about the triangle inequality theorem, that 2 sides need to be bigger than the third side, and find out a range of values that we could have for this third side in a triangle if we knew that a triangle had a length of 12 and a length of 8. What could be the possibilities for the third side? Well, we could know that the 2 sides, x and 8, well, those have to be bigger than the third side, so x plus 8 have to be greater than 12. If we solve that inequality, subtract 8 from both sides, we know that x would have to be greater than 4. And that would be the situation where these 2 sides are stacked right on top of each other. So we have x plus the remaining 8. So we know if it's 4 and 8, this side's got to be a little bit more than 4, otherwise they're stacked right on top of each other. Then finding the largest values of x. Can I move my face here? let's see, so 12 plus 8, these two sides, the other two sides have to be greater than x. So 12 plus 8 is 20, greater than x. This would be the case where the two sides 12 and 8 are extended as far as they can. Third side would now have to be slightly less, otherwise it would be stacked right on top of it. So our range now will be all values greater than 4, but less than 20 when I combine these two inequalities. So we know our triangle would have to be between 4 and 20, somewhere in that range. And maybe you can see a connection there, that if I take the two sides and subtract those two sides, that gives me the lower end of my range. And if I add the two sides, 12 plus 8, that gives me the high end of my range. So 12 minus 8 is 4, 12 plus 8 is 20. That gives me the range of values that I could possibly have between 4 and 20. And finally, let's look at what's known as the Hinge theorem. So we're going to take a look at another connection between triangles. And within this Hinge theorem, we're just comparing side lengths and angles. So it's similar to that connection we had before with the side lengths and the angles. So let's say that we've got a hinge, a door. Okay, so you've got your door frame and the door that opens in there. So the door frame and the door. So if I've got my door frame opened up, and let's say in this case my door is opened wider. So what's the connection between the angle that the door is opened? I think it's pretty clear that if the door is the same size and the door frame is the same size, they're both the same size compared to each other, that the one that isn't open as much would have a smaller angle than the one that is opened wider. And that's the connection that we have here. So if I have two triangles where the side lengths AE and BF are the same, AC and BD are the same, but this one's opened more, it's got a greater angle. So the third side of that triangle from E to C is greater than from F to D. So the distance that that door is open is further. And then the converse of that would be true. If this door has a shorter distance from point E to C than this one from F to D, then I would conclude that, well, this angle needs to be smaller because it isn't opened as much. The hinge is smaller. Okay, so you might think, well, that's kind of common sense thing, but that's something that we can apply when we're comparing triangles. So if we take a look at the problem that we have here, we want to use the converse of the Hinge theorem to help us out. So given ST is congruent to PR, how does angle PST compare to angle SPR? Let's take a look at what we know. So we know that ST and PR are congruent, and within this triangle they both share side SP. It's reflexive in both triangles. You can kind of see triangle RSP, and we've got the other triangle, so you can get a different color right here. Those triangles are congruent, or not congruent rather, but they share two sides that are congruent. And if they share two sides that are congruent, this is like the door frame and the door frame and another door over here. This one is opened a further distance than this one. Therefore, the angle across from it, or opposite, is greater. So I would say that angle PST would be greater than angle SPR. And hopefully that makes sense and you can visualize that. And then we've got some notes here on the Hinge theorem, the converse of the Hinge theorem that I believe I printed off for you that just verify what we said. If we have two sides the same, if one angle is bigger than the other one, opposite side, WX is larger. If we have two shared sides the same, and the third side is bigger, opposite angle will be bigger. So we explored the Hinge theorem. We took a look at triangle inequality theorem to find different measurements of the third side of a triangle and find possibilities for triangle side lengths. And we also compared triangle lengths to show where the longest and shortest sides are. That's all the time we have. See you next time.